I'm going to give an overview talk for ACTS for all the ACTS developers. I would start with some background and motivation of ACTS. As we probably know that at future colliders such as the HLHC, we have much increased combinatorics due to the high pi-up. And this means we will have much increased the CPU. As illustrated by this plot here, the CPU consumption will grow rapidly at Atlas Run 4 over the flat budget model. And the combinatorics also means much increased tracking instruction time with a much more complex tracking environment. So we need to find all possible ways to minimize the CPU and also speed up the tracking instruction, but not compromising the accuracy. So for the very first thing we can think of to use the efficient tracking, fast tracking strategy, we can either exploit the optimization of the traditional tracking algorithm, such as done at Atlas, but also could use the fast tracking techniques, such as using the ML techniques. We would also ensure the thread safety of the code to allow concurrent execution of the event. And at last, we can benefit from the hardware architecture, such as the multi-core and accelerator. So with all of these considerations in mind, ACTS tries to make itself a performance tracking software. And next slide. Okay, some reminder of the ACTS. So it's basically a tracking toolkit on top of modern computing architecture. So it's written in C++17. It's designed to be experiment independent, but targeting at the future hadron colliders such as Atlas Run 4. And some history is that it's based on the Atlas tracking code, but with all of those long problems of Atlas tracking code, it's just trying to improve the performance by ensuring the very rigorous thread safety of the code. And also, we are very careful about the event data model to consider the memory allocation and etc. And we have very rigorous unit testing to ensure the quality of the code. And to facilitate the integration into software framework, we have the very minimal external library dependencies. And also, we have in mind the usability and the maintenance of the code. But in addition to that, ACTS is also an open source platform for both the new tracking algorithm and also the hardware architecture. And our good news is that we have recently migrated from the GitLab to GitHub to allow for external contribution. And this slide here is an illustration of the ACTS components. We have the ACTS core, which is the main repository, and then we have in the ACTS core we have different tracking components such as the event data model, and the geometry, the track parameter propagator, and the different tracking features. We also have the fast simulation engine, the ACTS FATRAS, and the test framework, ACTS framework. These are two standalone repositories before, but now recently they have been integrated into the ACTS core to ease the maintenance and performance monitoring of the code. And here, this is incomplete list of the ACTS developers at the moment. So for the rest of the slide, I will go through the different components and also some detector application and R&D going on with ACTS. So the first, this is the tracking geometry with ACTS, which is the simplified geometry from the full simulation geometry to consider the CPU consumption and also the navigation. It's based on the Atlas tracking geometry concept based on the service. A new feature of the tracking geometry is that we have recently implemented our polyhedron representation for all the surface type. And this would in principle allow for fast navigation through the triangular mesh of all the surfaces. And implemented detector geometry, there's not so much change with this. So we support the silicon calorimeter and the muon spectrometer for this. And one thing to mention is that we have different plugin to transform the external detector description into the SCTS language through such as the digital FTGeo and GeoModel plugin. Since we have to consider the material effects during the tracking, the material have to be stored in a way. In SGS, this is done based on either the surface or the volume. And we have the material mapping tools for this purpose, which can map the full detector material onto either the surface or volume, depending on the detector type. So for example, for the discrete detector layout, such as the silicon detector, the material can be averaged onto the closest surface, and the material effects will be taken into account when the surface is passed. And for the continuous material distribution, such as the calorimeter, the material is mapped into the 3D grid points, and this material effect is taken into account at each integration step. So these two plots here are trying to validate the material mapping tools of NZTS. For on the left, the surface volume, the surface material mapping, and on the right, the volume material mapping. On the bottom, we can see the ratio between the mapped tracking material over the Gentile recorded material. And okay, so to propagate the track parameter, we have a highly template propagator for this, which can handle different user scenarios, such as different magnetic fields and tracking geometry. And we also support a highly customized execution and abortion at each integration step. So for example, we can have the material interactor and the common actor at each integration step. And for the stepper, we have different steppers here, as you can see. But basically, we are using the eigen stepper, which is the atlas stepper in region eigen as the primary stepper. And we will support the extension tool for the transport in the dense volume, such as the calorimeter. One thing to mention here about the stepper is that we have integrated the timing information in this, which can allow intrinsic timing measure. For the even data model for the track parameter and the measurement, we are using the fixed size eigen matrix to describe this. And this can be used to speed up the algebra calculation. And for the track parameter, this is there's not too much change for this. But now, as you see, we have the timing information integrated in the track parameter. We also support multi-component version of this. And for the measurement, we have a source link to the original detector element, which can be transcribed for other detector measurement description. And then to contain different measurement dimensions, we are using our STD variant for this. So the track state is designed based on the concept of the common filter. So we have the parameter part and the measurement part. This is not, there's not so much change with this over the past few months. But one thing to mention is that it's the track EDM, which is basically a container of the track states. So we have a very dedicated designed track state EDM for this, for the container of the track states. So in the past, we're using the STD vector, but now this is the SDS multi-trajectory. So it's eigenarray based, and we have the separate storage for the parameter coefficients and the covariance, and we keep track of the storage index. So in this way, we can have the parent relationship of those track states, and this would allow for very lateral splitting of the tracks. And another big advantage of this is that we can avoid the storage duplication for the shared measurements and parameters for this with this track EDM. So for the next few slides, I will talk about the track fitting and the track finding. So the common feature has been in ACTS for quite a long time, but over the past year, we have done a lot of optimizations on this. And it's used as an actor in the propagate as said before. And the common feature in ACTS now supports the whole search and the outlier rejection. And we also have a different approach for the smoothing with either the smoothing matrix formalism or using the backward propagation approach. And we also have the line Gaussian extension for this. And so this plot here are trying to validate the fitting resolution with the common filter. One thing to mention here is that this is not very perfect Gaussian because we have very little material for the track ML detector to justify a Gaussian pool. And these plots are the fitting efficiency and the some timing test. So we are validating the performance with the track ML detector as set and with PT down to 100 MeV and the eta in the before, smaller than 2.4. So as we can see with the red dot here, which is the results with the single muon, we have effectively 100 efficiency. And this pink dot here is for the TG bar results. We see some efficiency loss. This is because the impact parameter smearing. So the impact parameter smearing can get very worse. The resolution can get very worse for the TD bar events. And this is the fitting time versus the PT. As we can see, we have 0.2 milliseconds for one track, and the different color here, the different smoothing approach. So the common filter fitting is very fast. So if we go to look at the track finding in CTS, so currently we have a combinatorial seed finder for the track seeding. This is, there's not too much change over the past months, but one thing to mention is that the ACTS track seeder is highly parallelized. Is highly parallelable because we have the search for the top and the bottom space point very independent for each middle space point. And for the combinatorial common filter, this is really a new feature developed over the past months. And basically it's a merge of the track fitting and the track finding. And the difference between the CKF and the common filter is that we allow the track branching for this case. And the user can define the different measurement search and the branching strategy. We also allow the stopping of the bad quality branch to save some time. And this is the very preliminary results with the CKF we have. So the track finding efficiency and the fake rates are defined based on the recall and truth matching probability like this. And also there are some very simple track selection based on the number of hits and also the eta region. And currently we have the results this is the result for the TD bar, and we are using two different selection strategy for the cluster. So we can, the red dot here is the selection for always the best measurement on the surface, and the pink is to select all the compatible measurements on the surface. So with the pink one, we can have higher efficiency, but of course the fake rate will be high. But one thing to remember that we don't have done any tuning yet on the track selection criteria, and we just select barely 5 hits for all of those tracks. So this is a very preliminary results. And also this is some timing results with the CKF. So actually, since the fitting is very fast, most of the time is spent on iterating all of those combinatorics. So for the next, we are planning to do some tests with some other detectors, since this is the trigonal detector, to validate the results. And we also can have some speed up through either the fast geometry navigation or some fast cluster selection strategy. So because currently the cluster selection is basically running on all of those clusters on the surface based on the chi-square. Okay, so the last point about ACTS itself is the contextual design to allow for concurrent alignment and calibration. So we are using an algorithm context object for this purpose, which can support even the processing with different alignment, calibration, and magnetic const. And we have validated these concepts by some test. So we have run some propagation tests to validate the contextual alignment and some track fitting tests to validate the calibration, the contextual calibration. So these are done with different alignment and calibration const with different threads. And okay, so here, these are two slides about the application to the detectors. So over the past year, we have implemented a lot of new detectors with ACTS, such as the Atlas ITK, this Phoenix Silicon, as Joe had showed yesterday, and then also the CPC detector and the Bell2 Silicon. There's quite some ongoing discussion to implement the new detectors, such as the SFH TBC, the Bell2 central driven chamber, and also the Atlas muon system. And this slide here is just to illustrate the propagation test we have done with the implemented detector geometry. So this is just to say ACTS is working for these detectors. Okay, so for the next slides, just to illustrate some R&D going on with ACTS. So in addition to the tracking toolkit, as said, ACTS also serves as a R&D platform for both for either the tracking techniques and also the hardware. So this slide here is just on some plots to give you an idea. The ongoing tracking algorithm R&D projects. You probably have heard a lot of such talks in the past 2 days, so I'm not going into detail about this. Okay, in terms of the hardware exploration to explore the speed up with the parallelism, we can either explore that with the multi-core or the accelerator. So actually, ACTS is supporting the parallel event execution with GV with many cores, but there's also some perspective to explore some intro-event parallelism. So here, for example, so this is the seed finder parallelized over different geometry grids, and this is the fitting parallelized over different tracks. So as you can see, with the increase of the number of threads, we can see some speed up of the either the seeding or the fitting, but this is very limited by the hardware. And for the GPU, there are actually quite some efforts going on in the past few months to explore the accelerated tracking with the GPU. So currently there are two offloadings being explored. The first is the seed finder, and with both the SQL here and the CUDA here. So as you see, with the kernel executing the search of the top and the bottom darkly for the middle space point, we can see some very good speed up over the seed binding execution on GPU. And recently, we have started the efforts to implement our GPU-based common feeder as well. But this is not so straightforward. But we currently barely have managed to transcribe the ACTS propagator, the ACTS stepper onto GPU, and has seen some speed up as shown here with the yellow color. But this is very preliminary results and has not been optimized yet. Okay, so I have let's summarize my talk with some repository history of ACTS. So this is the repository history of ACTS. So in 2016, we have the first release of the code, and 1 year ago, we have the version 9 of the ACTS, and 1 year after, we have the version 19. And the ACTS members for this repository has grown from 27 to 50 over the past year. And as you can see here, there are a lot of commits going to this repository in the past year. And so the tracking toolkit, so this toolkit has expanded a lot over the past year. And there are a lot of optimizations going into it, such as the geometry navigation, the track parameter propagation, and even the data model. And particularly that we have new tracking features going into it, such as the track finding code, the fitting optimization, and the vertexing. As shown before, we have a lot of ongoing R&D efforts to explore not only the tracking technique, but also the hardware architecture. And in particular, that we have grown worldwide interest in STS contribution and application in the past year. So this is just a list of the institutes and experiments that are involved, which are not complete. And when looking to the future, that we are trying to facilitate the application to detectors and integrate into software framework, such as into the Atlas tracking software for the Run 3 and Run 4. And since, as said, we are working towards our full tracking solution in whatever. I think we are very close to do that because we have all of those track finding, track feeding, everything code there. But it's just that we need some more optimizations. Yeah. So that's all for my talk.
Great, thank you. Are there questions? Citing the CGP results. I guess I had one that more clarification on. I think it was slide 13. I realized after staring at this for a while, I didn't understand the idea of the way you've defined finding efficiency and fake rate, which is one is sort of one minus the other. It's more a purity and I guess, instead of an efficiency. I was curious what you meant by that.
No. Because is the ratio between the record over the truth. So the efficiency is defined over all of the truth particles.
Oh, I got it wrong. Okay, got it. And that makes more sense. Okay, yeah. Okay, thank you. Sorry, I misunderstood the numbers.
As a comment, this is of course a track selection of 5 hits is extremely loose for a HLLC environment. Yeah, I think Atlas is having 9 hits minimum as a track selection in order to control the combinatorics. And also the fakes. So this is really to push everything into the system and see how it behaves, which I think is a good first step.
Oh, definitely. But that is that to say that so this is the one plot where the efficiencies are not sort of spectacular, but it's hard to compare them with what you expect on this data sample, of course.
Sorry, could you repeat?
Yeah, what got me looking at this was the efficiency graphic. Sort of goes between 60% and 100%, and which is different from the other plots. So I was just curious if that's sort of what you expect given detector acceptance or the track requirements.
Do you mean the comparison with the tooth fitting results?
For example, yeah.
Yeah. Okay. So because I'm using some chi-square cut to select the hits, so if we don't impose any cut on the chi-square of the hits, this means that we just include all the hits. The efficiency will be just 100. But since we have some cuts, we lose some hits and then with some efficiency loss.
Okay, thank you.
Yeah, so
Joe
really
has
depends on, sorry, so really depends on the selection criteria. And this is just some not random, but just very flexible
yeah, just some examples.
Cuts. Yeah.
Okay. Joe, you have a question?
Yeah, I was just going to ask a question on slide 14. I don't know if maybe it's too early to say this, but do you have a sense for how much you think this will speed up by exploring these geometry navigation and faster cluster selection options?
I think, for example, for the PEP at 200, probably we can lower down to at least 200 maybe, because this is very preliminary results. I have optimized the CKF a lot in the past 2 days, but this is the test still with the older results. So I've not tested with the new code yet, with optimized the container, for example, for the select cluster candidates. So yeah. I just need to update the plot.
To bring that into perspective, if you look at the fitting time is at 10 to the minus 4 seconds. Yeah, and you end up with which is a tiny fraction of what you see as a combinatorial finding time. So this basically tells you most of the time you spend in picking the wrong, so it's basically a selection optimization. Now, as I said already, the Atlas selection for this type of environment is 9 hits rather than 5. One can already, well, I can't do it in the head, but I can see the complexity being entirely pushed down. So that means the number of combinatorics and the number of times you need to multiply by the fitting time goes down massively. So I think that's actually factors and not just half or something, which we're talking here.
Sure. Okay. Yeah. Thanks. I was just curious.
Okay. Any more questions? Okay, so let's go back to Bei then, I think.
Yeah, I'm here.